Hello once again. Thanks for watching this video here, which hopefully you've had a chance to watch the first video that I put together, which was called something like Making Sense of Negative Exponents. My main point in that video, everybody, was that when you see a negative exponent on a number, what it means is repeated multiplication of the reciprocal of that number. All right? Repeated multiplication of the reciprocal is kind of the main point that I would like to convey to you about negative exponents. That's what they really mean. All right, so we're going to do some examples of working out and simplifying some problems with negative exponents in this. And we're going to start with some pretty basic ones and kind of work our way up to some pretty hard ones pretty soon here. So I would call these basic ones 5 to the negative second, negative 4 to the negative third. So, you know, you can use negative numbers with negative exponents just like with positive exponents. But all you do is make each one of those bases a reciprocal and then change the exponent to positive. So 5 to the negative second is equal to 1 over 5, the reciprocal of 5, squared. Negative 4 to the negative third is 1 over negative 4 to the third power, all right? And then when you expand those out, well, the first one's pretty easy. That's just 1 over 25. The second one, though, I just did this one here just to emphasize that negative sign on the 4 there. It's being raised to an odd power, to the third power. So you've got a negative 1/4 times negative 1/4 times negative 1/4. That's 3 negatives. That means that your answer is going to be negative. It's an odd number of negatives. So your answer is negative 1 over 64. So sometimes your answer is negative when you use a negative exponent. But not always. Like, let's do another one. Negative 2 to the negative 2 power. All right? Well, okay, let's make the reciprocal of the base. That's 1 over negative 2 and raise it to the second power. Okay, so it's negative 1/2 squared, and that's a negative times a negative, which is a positive. All right? So it all does make sense. It's very consistent with all our laws of numbers and laws of exponents. It's confusing, though. There's a lot to learn here. Let's do one more of what I would call a basic example there, and it really gets to the idea of a reciprocal. So 2/3 to the negative 4th. Well, what's the reciprocal of 2/3? Yeah, it's 3/2. So it's 3/2 to the 4th power. I included this example just to show that, you know, when you do raise a fraction to an exponent, you can think of it, if it's more convenient for you, to take that exponent and apply it to each to everything individually. So 3/2 to the 4th is the same as 3 to the 4th over 2 to the 4th. You can apply the exponent individually to the top and the bottom of the fraction, and that just expands out to 81 over 16. Okay, so there's some basic examples. Let's do a couple of, well, trickier ones, extra ones, okay? So let's say we have not just a number, but let's say an algebraic fraction raised to a negative exponent, okay? So I'm trying to be tricky here. But you know what? It's really not that tricky because you still do the same thing. You still make a reciprocal of that base, which is the fraction, and then raise it to a positive power. So it becomes 5y squared over 3x squared, and that is raised to the third power. So one thing to keep in mind there is that, once again, that exponent outside the fraction applies to every single thing inside the parentheses. 5 gets cubed, y squared gets cubed, everything gets cubed, so you end up with 5 cubed y to the 6th over 3 cubed x to the 6th. All right? So that's what it looks like, and that would be a perfectly good way to write that, that expression, although probably a lot of people would expand out the numbers and say 125 y to the 6th over 27 x to the 6th, and that would be maybe the way you could write it, okay? Now, let's do something that actually is a little bit different, because in this example here, you see positive and negative exponents kind of mixed up inside that fraction, all right? So we are going to learn something a little bit different with this example, folks, all right? So first, though, notice that there's numbers, x's and y's on the top and the bottom, and I would suggest that whenever you can do this, you handle all the like terms kind of at a time. So the first thing I would do would be to take care of the 2 and the 6th. 2 divided by 6 is the same as 1 over 3. So I know that on the bottom of that fraction, there's going to be a 3. Okay, so Then let's handle the x's. So you've got x to the negative second over x to the fourth, and hopefully you remember from your laws of exponents that you're going to subtract the top exponent minus the bottom exponent. All right, so negative 2 minus 4 is negative 6. So we'll have an x to the negative sixth in that fraction there, okay? And it'll be on top for now. Then when you handle the y values there, y to the fifth over y to the negative third, when you subtract those, 5 minus negative 3 equals 8, positive 8, and so you'll have a y to the eighth on your fraction. Now that could be an acceptable way to write that expression there, to simplify that expression, x to the negative sixth, y to the eighth, all over 3. However, there's kind of a thing in a lot of math courses and a lot of math teachers, a lot of math books, a lot of math tests, really don't want you to write an answer with negative exponents in it. So you should know how to write that same expression without any negative exponents. And all you're going to do is you're going to take that x to the negative sixth and kind of move it down to the bottom of the fraction. That's making a reciprocal, and turn the exponent positive. So y to the eighth over 3x to the sixth is, in most people's opinion, the preferred way to write that expression because it doesn't have any negative exponents in it. Okay? So let's do another example. Actually, before we do another example, I want to focus on that little trick right there. If you ever run across a fraction that contains factors in that fraction that are raised to a negative exponent, just move the factor to the other side of the fraction and then change the exponent from negative to positive. Okay? That thing that we did right there with the x in that last example, that's something you can do anytime you need to, all right? Just a couple of basic examples here just to kind of illustrate this point. A to the negative third on top could be a to the positive third on the bottom of the fraction, all right? That b squared on the bottom, that's a positive exponent, so it doesn't go anywhere. And you know, the a to the third on top moving to the bottom leaves behind a factor of 1. So it's 1 over a cubed b squared. Let's see if we switch that around. So we had a to the positive 3 on top, b to the negative second on the bottom. That b to the negative second would go up to the top of the fraction and become b squared. You don't really need to write it over 1, of course. I just threw that in there. I don't know why. And then if they were both negative, well, then you just switch places and they become positive, okay? So this idea about switching factors from the top to the bottom and changing negative exponents to positive exponents, that's just another thing to get used to, all right? There's a lot to get used to. It's kind of a confusing system. Let's do one kind of like extra squared, or extra problem, complicated problem, I mean to say. So we've got now rational exponents that are positive and negative inside a fraction, and the whole fraction is raised to a negative exponent, okay? So it's really, this is like a kitchen sink kind of problem. It's got all kinds of stuff in it. Well, I would recommend, once again, just for consistency in the video here, and there are other ways to do this, but I would recommend, just for consistency, to do the same thing that we've been doing, which is to take care of that big old negative 3 exponent outside there. Just write the same stuff in that fraction as a reciprocal. So that's a big challenge right there, switching places with everything. Make sure that you're, accurate and you don't, make a typo of any kind. So notice the fraction there, that a to the 2/3 on top becomes a to the 2/3 on the bottom. That c to the negative sixth on the bottom becomes c to the negative sixth on the top. So we're not changing any of the signs of the exponents inside the fraction. We're just making a reciprocal of that fraction, and now the exponent outside is a positive 3. Okay, so now we'll deal with the exponents, let's just say for a, and we're going to do the same thing that we did before. Just subtract negative 5/3 minus 2/3 is negative 7/3. So we got a to the negative 7/3 in our fraction. All right, let's do that same thing for the b. 1/2 minus negative 3/2 is 4/2. Okay, just because, remember, subtracting a negative is like adding. And by the way, 4 over 2 simplifies down to 2, so that is just b squared there in that. So that's our next one. And then the c's, we do the same kind of thing. Negative 6 minus negative 2 is negative 4. And so we have c to the negative 4. Now we're going to raise that whole mess to the 3rd power simply by multiplying those exponents together. So Negative 7/3 times 3 is negative 7. And 2 times 3 is 6. And negative 4 times 3 is negative 12. So there's our answer, a to the negative 7 times b to the 6th times c to the negative 12th power. And once again, if you needed to write that expression without any negative exponents, it would look like this, just by moving the negative ones down to the bottom of the fraction. Now, in this example right here, you could make an argument that the one with the negative exponents is better because it doesn't have any fractions. If you don't like fractions, then maybe negative exponents are better. However, if you really don't like negative exponents, then you got to be willing to put up with fractions, okay? So it's kind of one or the other. And really, it's about fluency, folks, is that it's not that there's one is right and the other one is wrong. It's that they're both the same. And your job as a student is to become as fluent as you possibly can with all these crazy notational systems that we have in mathematics. This particular notational system is a tricky one. It's not an easy system to learn. It takes practice, okay? And I know you guys are really good at practice and you understand the value of doing good practice. So I encourage you, do good practice, do good math, and be well. Again, thanks for watching this. Bye-bye.